Okay, so today we're going to be talking about operations with sets. The title of this section is Operations with Sets. At the top of the last lecture, 2.2, I mentioned a type of Venn diagram that intersects in this way, and I must have done at least one example with two sets intersecting this way. Now, the focus of 2.2, though, was really on sets that are intersecting this way, things that are subsets of each other, or proper subsets of each other. So this was covered in 2.2, this kind of relationship. But what about this kind of relationship, where these are not subsets of each other, they're intersecting just a little bit. One is not completely encased in the other. So this is going to be the focus of this 2.3 section. Sets that intersect in this way. Okay, and what we call this area is we actually call it an intersection. We call this area an intersection. And we have a symbol for it. There it is. It's like an upside down capital U. Is called the intersection of A and B. Now, let's be technical. How do we write this in set builder notation? Set builder notation. A intersect B equals the set of all things X, so elements X, such that, now how would you describe this area right here? How would you describe elements in this area where these two sets are intersecting? I would say it's things that are in A and things that are in B, things that are in both A and B. So what we'll say is we're going to use our symbols from 2.1. X is in A, so remember that little symbol, that little, like a C with a, it's almost like a backwards 3, sort of. X is in A, and X is in B. That is the set builder notation for this intersection. Whoa. So what we have is we have a picture of A intersect B. I'll get rid of that question mark now that we know what to call it. It's a picture, symbol, right? The symbol to say what it is. We have a verbal, not verbal, but I guess just a colloquial, just a regular statement of what that symbol means. It's the intersection of A and B, where things that are in A and B at the same time, and then we have the set builder notation for that. Okay, so let's do example 1. Example 1 from notes. So this is following from the lecture notes that are available in Canvas. It says to find the intersection of the sets A and B. I'm going to shorthand this, so find intersection of A, which is equal to the set of letters that spell the word number. Well, numbers, so with an S. So 7 elements in A, so I could say the cardinal number of A is 7. And B is the letters that spell the word rule. So 4 elements in that set. The cardinal number of B is 4. But they want us to find the intersection, so this is what we want. We want A intersect B. And let's give it in roster notation. Because there's so few elements here, we can easily list these elements. So, what elements are in both A and B? Well, R is in there, is in A and B. U is in A and B. L is not, right? L is in B, but not A. And E is in both of them. Okay, now as a picture, what would this look like? So this is fine. This is the answer. Set A intersect B is these three elements. But what would it look like as a picture if this was A and this was B? Whenever you're drawing a picture like this, you always want to start on the inside. Start in that innermost intersection right here. We'll put those three letters in there. R, U, E. That's the intersection. What's left in B then? Look at this, B, R-U-L-E. So what do I write inside of B here? Do I write R-U-L-E? No, I only write L. I only write L because R-U-E is already inside of B, it's just over here, it's stored in this part. So I have all four elements in B. Likewise over here in A, I'm not going to repeat R, U, and E. I'm just going to put the N, the M, the B, and the S. Because the R, U, and E are already accounted for here. Okay. So this is what the picture would look like for representing the relationship between these two sets, A and B. Okay, so something went wrong with my camera, so I'm just picking up here with example 2. This is from the notes. I've got to say all this again. Okay, so suppose 92 people went on a trip to Colorado. Of those 92 people, 40 went hiking and 65 went skiing. How many must have done both activities? Assuming everyone did at least one activity, so no one sat out and did nothing. Okay, and then I rephrase the question in a more technical sense. Now, the first thing you may ask is, how in the world could there only be 92 total people? Because 40 plus 65 is more than 92. And the answer is that some people must have done both activities, right? Some people must be counted twice here. Some people must have hiked and went skiing. That's the answer. That's how these two could possibly add to be more than 92. So if we draw a Venn diagram, and actually, let me make sure my camera is still going before okay, it's still going. If we draw a Venn diagram of this situation, how about we call this side H for people who went hiking, and S for people who went skiing. Box around the outside, the universal set is the people who went to Colorado on this trip, the 92 people. Okay. Okay, so the way we're going to do this is we're going to think about this circle, the H circle, the hiking circle, should add to 40. In other words, there's going to be some number that gets written here, the people who strictly only went hiking, and some number that gets written here, the people who did both hiking and skiing. And together, those two numbers should add to give 40. And likewise over here in the S circle, the skiing circle, the same number will be here, and then whatever this is, those two numbers should add up to give 65. So here's what we're going to do. We're going to say, to figure out what this center number is, we're going to say, well, we're going to say that if everyone did an activity, then we know that we can subtract 92 from the total here, 105. 40 plus 65 is 105. And this number will be how many must have done both activities. So we can subtract here, and we'll get 13. We'll get 13. This is the number of people that did both activities. So that's all we need to do here. And now, that actually is what the question is asking, so at this point we would be done. And if we wanted to be absolutely technical in our answer, we would say H intersect S, what did they want? They want the size of this intersection. How many people did both? But if I want to say how many are in this set, I need the cardinal number. Remember, the cardinal number is those two bars. Kind of looks like absolute value bars, but they mean the cardinal number, the number of elements. So the cardinal number, the number of elements in this intersection of these two sets is 13. So really what I should have is, well, that's fine. It's fine to have a 13 here because it's understood that these sets are numbers of people. So that's okay. Remember, that was an issue in section 2.1, being careful with, if you've got a set of letters, then you need to specify, if you're putting a number inside the picture, you need to specify that that's a number of letters by using this notation with the cardinal number. But since here the sets actually are a number of people, then this is fine. Now let's go a little bit further than what this problem actually asked, because at this point we're done with the problem. But let's go a little bit further just so you understand what's going on here a little bit better. What number would be written here? Well, it would have to be, this whole circle, H, needs to add to be 40. So this number must be 27, because 27 plus 13 is 40. Likewise, over here, what must go here? How many people strictly went skiing and not hiking? Well, it must be 52. It must be 52 because 13 plus 52 is 65. Okay. Let's see what's next. Let's talk about the union of two sets. So what if we have a situation with overlapping sets like this? I'll just call them A and B. But I don't want to talk about their intersection necessarily. I want to talk about the entire everything that's going on here inside of both of these sets. We call that the union. The union of the sets. The union of the sets A and B. And we denote it with a capital U. Capital U. Now, it's actually not a U, it's its own symbol, but it looks very much like a U. It's actually, so here's the intersection symbol. This one's kind of bad. It looks like a V, it shouldn't look like a V. There we go. And then, so intersection and union. Okay. Okay. Sorry, 1 second. Okay, so A union B. That's the symbol, this is the picture, this is just what it means in English. It's the collection of everything, both in A and B, the union of things in A and B. Now the set builder notation is going to be the set of all elements X such that X is in A. Now remember, intersection was X is in A and X is in B. Back here. That was the intersection. That was this area. Has to be in A and B at the exact same time. So we can't say, we have to be careful about the use of the word and here, because in math, and is strict. It means you have to be here and here. So we can't use that word right here. It's tempting. You look at this and you say, oh, it's things in A and B. No, it's the things in A or B. Or is much less restrictive. Or is much less restrictive. It lets you be here or here. So if I was to say to you that you need to do, to get credit in this class, you need to do the homework and take the quizzes and take the final exam, then it's clear to you that you need to do all three of those things. It's strict. But if I said to you, you need to do the homework or take the quizzes, or take the final exam, then it's clear to you that you could just do one of those three and be satisfied in the course, right? Okay, that's not how our course works. You do have to do all three, just using it as an example. So or is much less restrictive. It says you can be out here, or you could be over here, or you could be in the middle doing both. If you did both, that would still be satisfying the or statement. So union, a union is everything in A or B or the middle. But we don't need to specify that separately here because it's understood if it's in A, then it's in the middle. Or if it's in B, then it could be in the middle as well. Okay, so let's do an example with this. Okay. Example 3. Is this from the text? Nope, it's similar, but this is my example 3 from the notes. I was going to color code all of these lectures, maybe using different colors for examples and whatnot, but it's just not going to work because my markers are going to die, and I'll have to be switching colors anyways, so that's okay though. You're big kids, you don't need color-coded notes. Well, I suppose it does help sometimes, but anyways. Example 3, from the notes, let A equal 1, 2, 3. So we're going to let A equal 1, 2, 3, the set containing 1, 2, 3. B is the set 3, 4, 5. C is the set 6, 7, 8. Okay. We have some questions. Part A says to find A union B. Okay. A union B. Well, I will do a different color for my solution here. A union B is going to be a set. I want to combine A and B. Notice they have a shared element. I am not going to repeat that element. I am going to write it. I'm going to write 1, 2, 3, but I'm not going to write 2 3s because it's the same element. 4, 5. There it is, A union B. For practice, for extra practice, what's the cardinal number of A union B? 5, because there are 5 elements. Okay, how about part B? Find A union C. A union C is going to be the set of all things in A or in C. So 1, 2, just kind of gluing the sets together. There we go. And just for extra practice, it didn't ask for this, but what is the cardinal number of A union C? 1, 2, 3, 4, 5, 6. 6 items, or 6 elements. You get it. Good. What is A union B union C? Sorry, that's supposed to be a union. Sometimes my union symbols, whoops, sometimes they look like V's. A union B union C. So we want to do all 3. Well, all we do is combine all 3 of these sets. It's like a set addition, almost. It's kind of like adding the sets together, in a way. So we would say A union B union C. But you don't want to repeat elements. So I'll say 1, 2, 3, 4, 5. That's A union B. Now all the things from C, 6, 7, 8. There we go. And just for extra practice, what is the cardinal number? There are 8 elements. So there's the cardinal number. What else does it ask? Part D says find A intersect B. So the upside down U means intersect. So I want the intersection of A and B. But remember, A was the set 1, 2, 3, and B was the set 3, 4, 5. So take away the things that they don't share. What is that one element that they share? It's a 3. It's a 3, right? That's the only element they share. So what is the cardinal number of A intersect B? 1. That's a 1. Because they only have, because there's only one element in this set. Finally, part E says find A intersect C. Now look at A and C. A is 1, 2, 3. C is 6, 7, 8. Do they share anything? The answer is no. So what is in the set? Nothing. So what is the set? It's empty. The empty set. Because they share no elements. There are no common elements between A and C. So their intersection is empty. And by the way, what is the cardinal number? It's 0. If a set is empty, then its cardinal number is 0. Okay, cool. Example 4. Let's do some more examples with more set operations. So these two set operations, union and intersection, they're almost like addition and subtraction with regular numbers. Not really though, but this kind of. So what we're going to do is we're going to do more practice with these operations, just like you would do when you first learn addition and subtraction. You're going to start doing practice with bigger sets, bigger numbers, and longer expressions. So example 4 from notes. Let U be, wait, I think I'm getting lost here. Oh, no, yep. Okay, so the universal set, let U equal, so that's the universal set, it's not the union symbol, this is an actual set by itself. Set of all elements X such that X is an English alphabet letter. So, A through Z. Okay. Let M be the set of the letters that spell math, so M-A-T-H. So it's not the single word, it's 4 distinct letters. And N be the set that spells money. And what's K be the set that spells investor. Okay. Part A says to find, and now we get some interesting questions. M union parentheses N intersect K. Now, you know how grouping symbols work with addition and subtraction. Okay, so this is the second time my camera has randomly stopped, so I'm going to have to, oh god. Okay, so I got pretty far before I realized it had stopped. So let me pick up with where I think it stopped, which is with this example 4 from the notes. We've got these 3 sets with our universal set being the whole English alphabet. We were told to find this M union intersection of N and K. So we're going to use our knowledge of how grouping symbols work. It's going to work the same way here as it does with operations with real numbers. So we're going to find this first. N intersect K. That means finding the common ground between this set and this set. And I found it to be the letters O, N, and E, because those are the only 3 letters they're sharing there. So they don't share the M, they don't share the Y, and that's it. So we can start with you can compare with the smaller set, right? Makes it easier. Now what we do is to find the entire thing, we glue this set, O-N-E, which is living here, we glue it together with the set M. In other words, we write all the things from M, and then we write all the things from this set, we add them together, we glue them together. The only thing we need to make sure of is that we're not copying any repeated letters. But there are no repeated letters here between M-A-T-H and O-N-E, right? So no need to worry too much there. Okay. Now the second one, let me do that. The second part of this example said to find the intersection of M and this set, which is the union of N and K. So first, find the union of N and K. That means take the set N and the set K, glue them together. Now, they do have common letters, so we need to make sure we don't double copy those. So take a second and see if you can get those letters written down. And this is the set you should get for N union K. So we're starting on the inside here, N union K inside this parentheses, grouping symbols here. So I wrote all the letters from N, which is M-O-N-E-Y, and then I wrote the letters from K, but I'm not double copying that O, N, or E from the word investor. So you notice the N is missing, the E is missing, and the O is missing, because it's already been written here. You don't want to double copy those letters. Now what I do is I want to complete this problem, I want to take the intersection of the set M, which remember was the letters M-A-T-H, and intersect it with this set. What letters do they have in common? Well, just the M and just the T. The A from math is not there, and the H is not there in this set. Oops. So their intersection is just that set MT. And as bonus, what is the cardinal number? What is the cardinal number of this set? Well, it's just 2, because there are only 2 elements there. Okay. Next thing was disjoint sets. So a vocabulary word that we're using here. And it's a vocabulary word that you'll find yourself using in regular conversation, even outside of math. 2 sets are disjoint if they share no elements. Okay, so that's more of a general colloquial way of saying it, not getting too technical. It's not even really that mathematical, right? 2 sets are disjoint if they share no elements. Okay, getting a little bit more mathematical here. 2 sets are disjoint if their intersection is empty. So this says the same thing. I'm just getting a little bit more technical here. Their intersection, because now we know what intersection means, right? So they're disjoint if their intersection is empty. That means they share no elements, sure. Even more technical with math symbols. The sets A and B are disjoint if A intersect B is empty. So it says the same thing. Their intersection, which is A intersect B, that's how we say the intersection of these sets, is empty. Okay. 3 different ways to say the same thing. Now, example 5 from the text said to give examples of disjoint sets. So I encourage you to try to come up with some examples of disjoint sets. Just, it could be anything. 2 sets that share no elements. You can get creative if you'd like. My examples were the sets A and B. A being the set of all natural numbers, elements, so remember this is set builder notation. The set of all elements x, such that x is a natural number, and x is less than 4. So what numbers is that? The set of natural numbers is just 1, 2, 3, 4, 5, 6, etc. The set of natural numbers that are less than 4 is just 1, 2, 3. Okay, so the set A is just the numbers 1, 2, 3. What about the set B? It says all numbers bigger than or equal to 4. So this is the set of natural numbers 4, 5, 6, 7, 8, etc. 9, 10, 11, all the way to infinity. So they share no elements. They're very close to sharing elements because this is 1, 2, 3, and then this one picks up at 4. But they're distinct, they're disjoint. There is no common element in these 2 sets. So their intersection is empty. Another simpler example I gave was the set X being just the two elements A, B, two letters A, B, and the set Y being the letter Z, clearly these are disjoint. They share no letters. And quick example said, given these two sets, X and Y, find the cardinal number of their intersection. In other words, how many elements do they share? How many elements do they have in common? And you can kind of just look at these, since they're already listed, and say how many elements they have in common, right? First, what I did is I actually found their intersection. So their intersection is the numbers 4, 8, and 12, because those are the numbers they have in common. But they wanted the cardinal number of their intersection, and the cardinal number of their intersection is 3. So you don't have to find the set first necessarily, because it's fairly easy to just look at these and say, oh yeah, 4, 8, 12, that's 3. But I just like to be complete in my answers, excuse me, and write the entire set first, and then write its cardinal number. Okay, so I'm going to watch my camera more closely this time, because it is not fun redoing all of this. Okay, so where are we at? We are at De Morgan's laws. Okay, De Morgan's laws. De Morgan's laws. Alright, so these are a couple laws dealing with operations of sets and complements of sets that are pretty interesting. I'll just get straight to it. This is what they say. If I take the union of two sets, and these are any two sets, if I take the union and then take the complement, that is the same as having the complement of the first one intersected with the complement of the second one. Okay. We'll call that De Morgan's law number 1. There are two laws here. Let's see if this makes sense to us. Let's recall what complement means and everything. Let's do a little proof of this. Here's what we're going to do. I'll get a little bit of coffee first. Okay, I've got two arbitrary sets, A and B. I'm going to, on this side, I'm going to try to draw what's happening here. And on this side, I'm going to try to draw what's happening here. And if the pictures match, that will have convinced me that this is a true statement. Alright. Where'd my red marker go? There it is. Camera's still rolling. Good. Okay. A union B is all of the stuff in A or B, right? Let's get a picture of what A union B is. It's that. Right? Can we see that? Yes. This is A union B. But I want to get the complement of A union B. And remember, the complement of a set is everything that's in the box in the universal set, but not in the original. Right? So the complement's like the opposite. So I'm going to color everything in this box except for A union B. So that means I'm going to color in this entire box except for A union B, and A union B is just both of the circles, so I'm missing all of the circles. That's nice. So this over here, this means everything in the box but not in A union B. That's what the complement means. Remember, complement from section 2.2. That's what that means. Okay, so this is what the left-hand side looks like. Over here, I've got something a little bit more complicated. Oops. So I don't want to get my notes out of order here. I've got the complement of A intersected with the complement of B. What is the complement of A? How about this? How about this? Because this side's a little bit more complicated, I'm going to do it kind of in steps. So first, let me color in the complement of A. So remember that the complement of A is everything inside this box, but not the stuff in A. Okay, so I'm going to color in the entire box except for that A circle. So that means I'm going to get B. But I can't get that spot there because that's in A. So I'm getting all of this stuff. Whoops. All of this stuff. So everything except for that A. Okay. Now what about on this side? B complement is everything that's in this square or rectangle except for the stuff in B. So let me color code this. This is A complement that I've done in green. Now I want to use red for the final answer, so let's use orange for B complement. This will be B complement. B complement is everything in this square except for this B circle. Okay. Everything in this rectangle, I keep calling it a square, it's a rectangle. Everything in this rectangle except for the B circle. Now let me ask you this. Where are these the orange and green lines, where are they intersecting? Where is their intersection? It's everywhere outside of these circles, isn't it? It's all of this. It's all of this stuff. Everything out here is the intersection of the orange and green line. Oh, excuse me, the intersection of the orange and green lines, which is exactly what we have over here. It's just this picture looks much cleaner because this side is much easier to comprehend. So, they are in fact the same. They are in fact the same. So the red lines here represent the intersection of the green and orange lines. Cool. That's De Morgan's laws number 1. De Morgan's laws number 2 says kind of the opposite thing. A intersect B complement is equal to A complement union B complement. I think it'd be a good exercise for you on your own to try to prove these using pictures. Kind of do what I did. You can color code it. This is a time when color coding is absolutely great because you can really, it gets so complicated with all these lines. It's nice to have some colors there. So I'm not going to prove this for you, but I think it would be a good exercise for you to try to prove it yourself just using the pictures like I did. Something that will help you to remember how this works, though, is you can think of the complement symbol, so that little tick mark, distributing across the sets, the set operation. And changing unions to intersections and vice versa. Intersections, vice versa means like the opposite. So it changes unions to intersections and it changes intersections to unions. It kind of distributes, right? It's like you distribute this complement symbol to the A and the B and you flip the set operation in the middle. It's kind of a way to remember how these De Morgan's laws work. It's almost like a negative sign on the outside of a plus problem, the addition problem. A plus B with a negative on the outside means you negate both. Well, anyways, I guess a little, maybe not a perfect analogy, but you can think of these complement symbols as distributing and flipping that set operation, because that's what De Morgan's laws does. Let's do an example. This is example 6 from the notes. So let's just verify De Morgan's laws using these sets. Kind of showing that De Morgan's laws work at least with these sets. U, the universal set, is a set of all letters, English alphabet letter. Let's let A be the set of letters that spell hound, so H-O-U-N-D. Whoops. And B be the set of letters that spell rock, R-O-C-K. It doesn't always have to be words, it could just be random letters, but it's easier to remember, I think, if they spell words. Okay, verify that A union B complement, the complement of A union B is equal to A complement intersect B complement. So this is not going to be a proof of the De Morgan's laws. A proof of De Morgan's laws requires pictures that have arbitrary sets in them. These are just two random sets. It could be anything. When you've got two specific sets and you're going to show this property being true, it's not a proof for every set. You're just verifying that it does work for at least these two sets. Okay. Oh, let me make sure my camera's still rolling. Yes, good. Alright. Whoops. Let's find each of these sets. Let's find each of these sets. A union B complement. First, let's find A union B. So glue A and B together. I'm going to have H. Oh, let me just start with A. H-O-U-N-D. Now, what about B? Do I stick all R-O-C-K here? Almost, just not the O, right? So R-C-K. There we go. Alright, there's A union B, but I need its complement. I need the complement of this union, of this new set. Remember, the complement is all the things that are in the universal set that are not in this set. So what I'm going to do, this is going to be a little bit tricky, I'm going to write the entire alphabet, but I'm not going to write these. So I'm going to have A, B, alright, C, D, E, F, G, H, K, I, J, K, K is there, L, M, N is there, O is there, oh wait, and then P, Q, R is there, oops, so S, T, U, V, and then W, X, Y, Z. So if I'm not sure, what I can do is say, well, there's supposed to be 26 letters total in the alphabet, so this plus this should equal 26. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 plus 8 is 26. Good. So I didn't double count anything. Okay, that's this side. Now what I do is I find this side, and then I'll make sure that they equal each other. So I should say are equal to each other. A complement first is going to be all the things that are in the universal set that are not in A. Okay, so A, B, so I'm going to write everything except for these 5 letters. A, B, C, not D, E, F, G, H is not there, I, J, K, L, M, N, O, P, Q, R, S, T. U is in the set, and V, W, X, Y, Z. Okay, if I'm not sure, I could count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, plus these 5 is 26. Good, so I've got all the letters. So A complement is the set of all the letters in the universal set, which is all the 26 English alphabet letters, but excluding the letters that are in A. B complement is a similar thing. So I'm going to have 22 letters here. I'm going to exclude these 4. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. All right. So I've excluded those 4 letters. I've excluded those 4 letters, so there should be 22 here. Finally, what I do is I look at A complement intersect B complement. Which letters do they have in common, these 2 sets? Which letters do they share? Okay. Big sets to be doing this with. They share an A. They share a B. They do not share the C. Alright, this has a C, this does not. They do not share the D, because this has a D, but this does not. Okay, then they pick back up at E. Then F, G, no H, because this has an H, but this doesn't. Pick back up at I, J, no K, because this has it, but this doesn't. They both have an L, though. M, no N, no O, because, again, it has to be in both places. P, Q, no R, because this one doesn't have an R. So picking up at S, they both have S, they both have T. They do not both have a U, because this one is missing the U. Picking up at V, and then they share W, X, Y, Z. So, what I have is I have my right-hand side of De Morgan's laws right here. And I have my left-hand side of De Morgan's laws right here. Are these 2 sets exactly the same? Is this exactly the same as that? They both have, here's what I'm going to do. I'm going to go like this. They both have A, yes. They both have B, yes. They both have E, F, G, I, J, L, M, P, Q, S, T, V. And then they both have W, X, Y, Z. Cool. So what we just did is we verified De Morgan's laws for these 2 sets. Cool. Part B says to do the same thing in reverse. I will leave that to you guys because that is a long problem. I think that you can do it though. And you should especially feel good if you are able to prove that second De Morgan's laws using pictures like I did here. If you can do that, then you really have an understanding of De Morgan's laws. Alright, last thing says extra practice. Let's see what that's about. Use Venn diagram on page 70. So I've got my textbook here. Which Venn diagram? Okay, the one at the top. Which students played only tennis? Determine which students played tennis or volleyball. Which students played tennis and volleyball. Find the number of students that played tennis or volleyball. Let's do it. This is these are problems 30 through 33, page 70. With the Venn diagram. I'm not going to draw it, so it'd take too long to draw it. It's on page 70 in the textbook. The last few problems are near the end of section 2.3. So these are homework problems. So we've got a Venn diagram. First question is, which students played only tennis? So we've got some students living outside in the universal set. Hang on. We've got some students living outside in the universal set. They didn't play tennis or volleyball. We've got students that did play tennis are Will, David, Kim, Barbara, Holly, Jessica, Jeff, and Kent. But which students played only tennis? They didn't play volleyball. That would be Will, David, those people on the outside of the intersection, Kim and Barbara. Now, which students played tennis or volleyball? Well, that would be Will, David, Kim, because it says or, so they could be only playing tennis, or they could be in the middle, where Holly, Jessica, Jeff, Kent are, or they could be on the other side where they only played volleyball with these people. So, who played tennis or volleyball? Well, all of these guys. They played tennis, they played volleyball, and they played both. So, they all satisfy that statement. Which students played tennis and volleyball? Which students did both? Well, that's just the people in the middle. Find the number of students that played tennis or volleyball. Well, that's asking this question. It's just saying how many played tennis or volleyball. So you would just count these up. Cool. Nice little extra practice there. Alright, I got some problems marked that you should look at in the text. 1 through 5 odd, and 25 and 27. Those would be good extra practice in addition to your Hawks homework. Alright, that is it for 2.3.